So we are actually not going to do group theory today. We are going to just do, we have about 15 minutes left. So you guys have a choice. Do you want me to define what a group is or talk about the possible applications, or maybe talk about the possible applications and define the group in the next class?
I'd go with applications.
Okay, we have one vote.
Application.
Okay.
Yeah, applications.
All right, cool. So, why do we need group theory essentially, right? So this is a very incomplete list of applications. I should be able to spell applications, or apps as they call them today. So as a physicist, the first application is going to be on my list, quantum mechanics. Before quantum mechanics came around, nobody cared. Very few people cared about group theory in the physics community. But quantum mechanics, makes it mandatory. So essentially, the space of states of a quantum mechanical system form a representation of the symmetry group of the system. So for example, these symmetry groups could be the rotation group. So for example, either your quantum mechanical system has some rotational symmetry, or they are in a space where there's rotational symmetry, right? Because if you think about empty space, we do have rotational symmetry, right? We have, this is known as isotropy of space. So rotational group, and so the rotation group, you may or may not know, in 3 dimensions is SO3, but in quantum mechanics, it's the double cover, which we will basically learn what it is, SU2, which becomes more important. Okay, so you cannot understand the atomic spectra, for example, the atomic spectra without group theory, without understanding the representations of SU2. Okay, so for example, if I look at the hydrogen atom, there are going to be transitions. So say hydrogen atom or some other atom, or a molecule, there will be transitions, between states with, say, different angular momentum. So what do I mean by that? Look, for the mathematicians, essentially what I'm saying is that an atom can be, say, in a state where its angular momentum is 3 in some units of h bar. But then the atom can transition to a state where its angular momentum is 2 h bar. So it's losing its angular, a lot of energy in making that transition. So that energy is carried away by photons. whose energy is given by h bar omega, omega being the angular frequency of the photon. Now, the intensity of this photon will depend on the angular momentum, because you can show that the number of physical state for L equals to 3 is different from the number of physical state for L equals to 2, right? So there will be, so the number of transitions that are possible will depend on the angular momentum. And therefore, the relative intensity of different transitions will be different depending on their angular momenta, and you can't really understand that unless you do group theory. Okay, we will do this. We will derive the angular momentum representation of SU3. It's not just important physically, it's also important very mathematically, because a lot of the techniques mathematicians use in deriving representation theory starts from this problem. Okay, so that's one. So part of it is that the symmetry of space-time, or part of the symmetry of space-time, well, the symmetry of space-time is a group, it's represented by a group called the Poincare group. Okay, and quantum mechanics, and the particles, the fundamental particles, that we see in nature are representations of basically a subgroup of this, or let's say of this group, some kind of representation of this group. So what's interesting is that there are representations of this group that nature doesn't seem to use. Okay, so there's one of the, and there are quantum field theories, people have developed theories, physical theories based on those representations, but there is no particle in nature which obeys that representation. So it seems like, nature does not always use all the math that it could use, okay? And so we'll discuss about this classification of how different fundamental particles fall into different representation of the Poincare group. So these are very important applications in quantum mechanics. The second set of application, which is important, it's related to quantum mechanics, but slightly more in a general setting, is particle physics. And those of you who are mathematicians, don't worry, I will get to some mathematics application as well soon, okay? So in particle physics, the variety of particles that one sees in strong interactions, so strong interactions, also known as hadronic physics, can be understood as the up quark, the down quark, and the strange quark, furnishing a representation. Often I will use the shorthand rep for representation. It's kind of common in this business. So they form a representation of a group called SU3. Okay, and this was discovered by Murray Gell-Mann, and in his famous paper he published called the Eightfold Way. And he was able to even predict a new particle which was later found. So that's application 2, particle physics. So next I want to talk about some applications in mathematics. So topology and say differential geometry, okay? So there are these groups in topology called homotopic groups. And what are these groups? These groups are equivalence classes of maps. So they're written like pi of n. And they're equivalence classes of maps from the n sphere to some space n. Okay. So the homotopic group of that manifold M or that space M is a topological invariant. Of that space. Okay, so groups, the homotopic groups are very useful in classifying different kinds of spaces. Now, these are also important groups which are discrete. So not all important groups are continuous, of course. All groups are important. Homotopic groups are discrete. Okay, so this is from topology. From differential geometry, there are the two examples. One is the holonomy groups. And this is something we will study. So what are holonomy groups? Holonomy groups, they measure curvature of a connection on a manifold. Okay, so holonomy groups are important in understanding the curvature of manifolds. And they have very important applications in physics, especially in string theory. Okay. And lastly, Lie groups also describe continuous symmetries of manifolds. So for example, if I take a two-dimensional sphere, you know that if I take that sphere and put it, say, at the origin of a three-dimensional Euclidean space, so if I now rotate it, it'll, that's a symmetry, right? And all the possible rotation of the sphere form a group, which we will see is called SO3. But what people don't know is that there's also another group, which is the group of rotations in two dimensions. And that group is called SO2. But what we will show in this course is that the two-sphere can be expressed as a quotient. And I will define what the quotient is of these two groups. So we see that, these groups are very useful in classifying and describing symmetric spaces. The sphere is an example of a symmetric space. It's a space with lots of symmetry. Okay, I think I have just run out of time, and I will end the class here. But before we go, maybe we can just do a bit of we can have. Oh, it seems like I don't. Do I have the? I should have the list of students. Let me see. Okay, so it turns out that I don't have the list of students today. So I'm not going to take the attendance today, but I will take the attendance next time. So those of you who have to go, please go. But if you have to go to namaz or whatever, but I will take questions. So any questions? Okay, I think maybe people are all tired or some whatever. So I'm just gonna end the class here, and I will see you day after tomorrow, okay? And if you think that this was you want some difference, you want me to change the format of the lecture in some way, please let me know, okay? I'm stopping.